Okay, so we started with alkenes, and alkenes, we talked about alkenes, and alkenes had this sp2 hybridized carbon atom uh, with this pi electron cloud, which had a very high electron density. And we had started talking about the reaction mechanism. What was the reaction mechanism that we talked about bromination? Yes, we even did the reaction mechanism. We started talking about bromination. In bromination, what happened was that you had a double bond and bromine would get added to it. And that was used as a test for uh, identifying alkenes, which I did not write over here. Did I write somewhere? No. This was used as a test for identifying unsaturated hydrocarbons. Just one second. I think there's too much stuff on the board. So, so this one, Tika, I think I need to add this point. So it's used as a test for identifying unsaturated compounds, basically alkenes. And in the reaction, Br2 would get decolorized. The red brown bromine, it gets used up, and if it gets used up, there is no red brown bromine, so it decolorizes. Anyways, that's a test for identifying unsaturated hydrocarbons, and we talked about it. And we talked about the mechanism of this reaction. The mechanism was that bromine was a non-polar molecule, so it would get polarized, and heterolytic fission would occur. That the electrons in bromine would get repelled by the electron cloud over here. Uh, and the Br minus one would break away, and the Br plus one would take away all the electrons from the pi electron cloud and bond with one of the carbon atoms. The other carbon atom would get a positive charge, so the Br minus one that is broken away would then come in and would bond with it. And that was your two-step reaction. You had a carbocation intermediate that was formed. And this was the mechanism that you're supposed to write in your exams. And we talked about the two-step mechanism. So was this clear last time, Ethan, Mohammed? Is this clear? Isaac, clear?
Yes.
Okay, so the second one, what's the second reaction? We did bromination. The second one is known as hydration. Now, what happens in hydration of alkenes? So that's a reaction where an alkene, let's say ethene, it goes and it reacts with water molecules. As it reacts with water molecules, and the double bond, it's exactly the same reaction. The double bond would break, and on one of the carbon atoms, an H would get added, and on the other one, the OH group would get added. So water molecules are going to get added. And the conditions for this reaction were that you need a phosphoric acid catalyst. That was needed, and the temperature of the reaction should be 300 degrees centigrade, and one more, which is 60 atmosphere pressure. So, three conditions for the reactions that need to be remembered. Hopefully, everyone remembers something about this from O levels. So, H and OH would get added. The mechanism for this reaction is kind of the same. And remember, it's not just phosphoric acid; it could be any catalyst. You could also use H2SO4. Basically, you need an acid, uh, but phosphoric acid behaves in the best way. So this is hydration. Now, the mechanism of the reaction is quite similar. That you have an alkene. Now, because of the acid that you added, there's H plus one ions in the solution. These are your electrophiles. So these over here are your electrophiles. Electrophiles are the ones that are attracted to uh, they're attracted to the electrons in the pi electron cloud. So H plus one would definitely be attracted to those electrons. So your H plus one pulls the electrons in the pi electron cloud. Remember the double bond. It pulls the electrons from the pi electron cloud, and as a result, previously there was a double bond between the two atoms, the two carbon atoms. And when H plus one comes along, the H plus one is going to pull the electrons in the pi electron cloud, and it would pull them and it would bond with them. So H plus one pulls the electrons and bonds with them. And as a result, the positive charge on the H goes away because it has pulled the electrons away from the pi electron cloud, and this carbon atom over here would get a positive charge. It would become a carbocation. So that's your carbocation intermediate that is formed. Right? Mohammed, is this clear? Ethan, is this clear?
Yes.
So here's your carbocation intermediate and the next step. What's the next step? Now you've added water, right? Water has lone pairs. And the lone pairs on oxygen have a very strong partial negative charge. So the next step is these lone pairs on water, they're going to get attracted to the carbon over here. And when they're going to get attracted to the carbon over here, the positive, there's an H over here which is also positive. I mean, both these hydrogens are positive. So the H would eventually get repelled, and it would break away because it's going to get repelled by the positive charge on the other side. So, anyways, the first step is so this last step is kind of irrelevant, but it would have two steps. You had carbon and H. The first H had already attached itself, the H plus one. Now the water is getting attached. When the water molecule gets attached, what happens is water loses its lone pair. Because why does it lose its lone pair? Because the lone pair is now attracted to the carbon. It's now pulled towards the carbon and bonded to it. So the lone pair is missing, which is why this oxygen is now going to get a positive charge. So in the last step, oxygen needs its lone pair back again. So it pulls electrons, and let me. Okay, so the last step is that the oxygen needs its lone pairs back again because carbon took it. It's going to pull the electrons from H. That's your last step. So the final step is that you have carbon and H. There's an H already attached, and there's your OH that's now attached because the H plus one has broken away. And your oxygen gets its lone pairs back again. So let me just briefly explain what happened here. Okay, it just added these. We just have these extra last steps, which are not very important. H plus one from the acid comes along and pulls the electrons from the pi electron cloud, bonds with it. The pi electron cloud is now bonded with H. The carbon gets a positive charge. The lone pairs on water are then attracted to the carbon atom over here, and the lone pairs are attracted to the carbon atom, and the lone pairs go and bond with the carbon atom, which is why the lone pairs are missing over here now, and oxygen gets a positive charge because of that. I mean, carbon gets its electrons, but oxygen now lost its electrons. So the oxygen pulls electrons from H, so the H breaks away, and that's how the H is reformed. You started off with H plus one, and that H plus one is now reformed. Is this clear to everyone?
So in
Yes.
the exam, do we write the third step or do we just skip to the fourth step?
Then you're going to write the whole step. Uh, or what you could do, I mean, you're going to write the whole step. Usually, what happens is that in your exam, this mechanism usually comes. I mean, they're both pretty much the same. Uh, this mechanism doesn't really often come, but it can. I mean, you can be asked questions about it. This is also, remember, electrophilic addition. I mean, it's the same mechanism, exactly the same mechanism. So this one is also electrophilic addition, and you're going to write the whole mechanism. Take it till the end. Most of the time, what happens is that they draw the first step and then they draw the last step and then they talk about the intermediate. TK. We're going to do the questions in a while. Once we're done with the alkenes. Uh, so you're going to look at exam questions, TK. Ethan, so the mechanism is
Just
clear, right?
another question.
Yeah.
What's the molecule's name for the third one?
Which one?
The third step molecule's name.
I mean, you're talking about this one?
Yeah. Oh, wait, no, the next one.
This one?
Yeah.
I don't think it has a name. I mean, it's just an intermediate that's formed.
Okay.
I mean, it's basically ethanol with the. I mean, ethanol is getting formed in the end, right? So I don't think intermediates usually have names. I mean, this is generally called a carbocation. TK. So I'll search, I'll check, but usually they don't have any names because that's not a functional group. Do you get my point?
Yes.
That's the next one. The next one is exactly the same. It's just I'm just going to quickly go over it. It's alkenes plus hydrogen halides, which are your HCl, HBr, HI, etc. molecules, right? So this reaction, nothing different, same as the ones before it. So you have an alkene, and there's an HCl molecule. Remember, the HCl molecule is already polar. There's a positive side and there's a negative side, and there are your lone pairs, sorry, your electrons in the middle. And what would happen is that the positive H would attract the electrons from the double bond, and the electrons over here are going to get repelled. So there's going to be hydrolytic bond fission. Next step would be next step would be that the double bond H from HCl would bond with the carbon atom. This would become a carbocation. The Cl minus one that has broken away, it's it's going to come in and it's going to bond with the carbocation. That's it. So you have H and Cl, right? So it's pretty much the same as the first one. Nothing different. HBr, HI, pretty much the same as this one. It's exactly the same as this one. The only difference is that the molecule, HCl molecule, is already polar at the start. So it's going to attack it in a particular orientation. The H is the one that's going to bond with the double bond first, and then the Cl minus one would come in. ठीक है? Is that clear, Ethan? Is this clear?
Yeah.
Now the last one. Uh, the last one is kind of different. The last one is known as, you can call it, it's heterogeneous catalysis, and that's hydrogenation of alkenes. So hydrogenation of alkenes. What happens in hydrogenation of alkenes? You have an alkene, an ethene molecule, and H2 is added to it. The conditions for this reaction are that you need a nickel catalyst plus 150 degrees centigrade temperature, and you could also use platinum or palladium as a catalyst. Pretty much any transition metal would do. Nickel is the best. Nickel is the one that's used most often. And there's going to be H and H and H, and the double bond would vanish, and there's going to be more hydrogens added, right? So that's what hydrogenation is, and that's also an electrophilic addition reaction. The mechanism, first thing, what's the importance of this reaction? The importance of this reaction is that does anyone remember where it was used? Hydrogenation of alkenes in O levels. Any idea? Mohammed, any idea? Ethan, Aiza?
What was the question again?
Yeah. The question was, do you know where hydrogenation was used in industry?
Uh,
Um, I'll just tell you,
maybe. Yeah.
it was used to manufacture margarine.
Oh,
I mean, I'll explain what happens uh, when margarine is manufactured. You had unsaturated vegetable oils. As you had unsaturated vegetable oils, which means these are your natural oils that you get from, and these are mostly seed oil, uh, like sunflower oil. So unsaturated vegetable oils have a lot of double bonds in them. What you do is you hydrogenate the molecule. So these are large, complicated molecules with lots of double bonds, and as a result, margarine is formed. Now, what happens if H2 gets added? When you add H2 to a molecule, and margarine is saturated. So the question is, what happens when margarine is produced? The size of the molecule increases slightly, but very slightly. It increases very slightly. So when that happens, you have more van der Waals forces. And when you have more van der Waals forces, uh, you have higher melting and boiling points. So that was a cheap way of making margarine. Margarine is solid and vegetable oils are liquids. They have relatively lower melting and boiling points. They're smaller in size, which means that they have less van der Waals forces. Mohammed, is this clear? Ethan, is this clear?
yep.
So that's how you solidify it. Margarine is a replacement for butter. So butter is harder to get. Vegetable oils are easier to get because you just have to crush vegetables, seeds of vegetables, and you can extract oil from it. So this was the alternative to butter that's obtained using hydrogenation. Now the mechanism of the reaction. The mechanism of this reaction is kind of very different. The mechanism is basically heterogeneous catalysis. So nickel is being used as a catalyst. In heterogeneous catalysis, you have two processes that are happening. One is adsorption, first one. Now, adsorption is that the catalyst forms weak bonds with reactant molecules. What happens in adsorption is, and remember it's with a D. So you have this nickel catalyst, and this is the surface of nickel. And you have this reaction happening where you have a double bond, and you have H2 molecules, right? Now, transition metals have this property that they kind of attract electrons very, very slightly, but very slightly. So the electrons in the bonds, they're going to get attracted to the catalyst. Remember, transition metals are somewhere in the middle of the periodic table. In the middle of the periodic table, what actually happens is that one second. So in the middle of the periodic table, what happens is the left elements like to lose electrons, but as you go to the right, electronegativity increases, and they start to atoms they start to gain electrons. Why? Because they have more protons, and that's one of the chief reasons why they start gaining electrons. There's a more positive nucleus on the right side. Transition metals are in the middle, so they kind of lose that tendency to lose electrons. For example, gold doesn't like to lose electrons. Gold doesn't really like to form ions. You have platinum; it also is not very reactive. Even iron is not very reactive. You can have things made out of iron, and iron is not going to react. It's going to take years for iron to rust, even. So they don't like to lose electrons. Instead, they have this very weak attraction for electrons. Is that clear, Ethan? Mohammed, is this clear?
Yes.
So the next step is, how would adsorption happen? That the nickel catalyst would slightly start pulling the electrons. So the double bond in the molecule would change into a single bond, and the pi electron cloud would be attracted to the nickel catalyst over here. And the same would happen to an H2 molecule. The electrons which were previously being shared between the two atoms, the electrons are going to be pulled towards nickel. So that's how weak bonds are being formed. Is this clear? Yes or no? Is this clear?
Yes.
Yep.
So weak bonds are being formed between reactants and catalyst. The next step is that is deadsorption, because these molecules have some kinetic energy, which means that they're flying around. So these molecules are going to eventually bounce back. I mean, the atoms are going to bounce back. When they do, the bonds that were previously holding them together, that they have now broken because of the catalyst. Uh, Now new bonds can be formed easily. So now what's happening is that you have an ethene molecule but without the double bond, and you have hydrogen atoms but without the double bond, and new bonds can now be formed. So this step is the final step is adsorption. Remember, this could be asked deadsorption. Sorry. So weak bonds between reactants and catalysts, they start to break. So is this mechanism clear? Mohammed, Ethan, is this clear? Is this clear?
Well, I'm
Yes.
a bit confused with nickel, the nickel and the
The
alkenes and hydrogen.
I mean, this part. Did you get the first part about
Yeah,
the periodic table?
where the nickel is a transition metal and
Yeah, I mean,
it loses electrons easier.
when you have a transition metal, what happens is how do I rotate this one second? Sorry. So we can talk about this. Just which page were we on? Okay, anyways, this one. We were talking about this, right? I told you that the left ones like to lose electrons and the right ones try to gain electrons. These are in the middle. They have more protons. I mean, so they kind of start to attract electrons. I mean, you have nickel over here. Nickel has a lot of protons. So if a molecule is passing by, it would weakly, very weakly try to attract its electrons. Ethan, do you get this point? Is that point clear?
Yeah,
So eventually what happens is that the pi electron cloud is going to be pulled or it's going to get attracted towards nickel. And the electrons that were being shared between the hydrogen atoms, they're going to be attracted towards nickel as well. So what happens to the bond? The bond has been broken, right? Between the H2 molecule. Ethan, is that clear?
yeah, yeah.
So so the activation energy is now lesser. Why? Because the old bonds have been broken or have become easier to break. And the molecules are flying around. After bumping into nickel, when they fly back, the old bonds are broken. And now you can form new bonds. Like this H could bond with the carbon, this H could bond with this carbon atom, right? Is that clear?
Um, all right, yeah. So
So
the nickel, uh,
yeah,
uh, the electrons go to the nickel and the double bond as well,
yeah,
the pi bond.
yeah. I mean, it's exactly something like this. Like what was happening over here? This thing. Like over here, you had Br positive that was pulling the electrons from the pi bond, right?
Yeah,
But now what's happening is that the electrons are being pulled by nickel. And one thing why catalyst transition metals are very good catalysts is that they only very slightly attract electrons. Unlike non-metals, if you had a non-metal over here, the non-metal would have completely pulled the electrons and strongly bonded with the carbon atom, and it would not have allowed the carbon to go back. So nickel is going to be very, very slightly attracting those electrons. So the bonds that are formed are not permanent bonds. They're just very, very weak bonds because nickel doesn't, I mean, it's a metal. Metals don't gain electrons. They just had, because they were transition metals and transition metals have more protons. So they just had a very, very slightly stronger attraction for electrons. Ethan, is that clear?
yeah.
So that allows the bond that has been formed to be broken back as well. And when it breaks, I mean, the first step of the process, which required energy, that has been done automatically. And the catalyst has helped us in doing that. So I can add that as well. So the catalyst reduces activation energy of the reaction by making it easier to break old bonds. Now, there's a thing that we're going to study. We did 4 electrophilic addition reactions. Okay, there was hydrogen halides, there was hydration with water, and there was bromination. So we're done with four. Now, one thing that we're going to study is what would happen if your molecule is unsymmetric. So unsymmetric alkenes and the addition reactions. First thing is, what is an unsymmetric alkene? Now, an unsymmetric alkene is this one. Where if you divide the molecule into around the double bond, the molecule looks very different. The left and the right side are very different. So that's what an unsymmetric alkene is. So the left side is different compared to the right side. Okay, so two totally different sides. Uh, Now, what is the problem? What happens? Let's say you have a propene molecule and you're reacting it with water. Two things would happen that if you reacted with water and you hydrated it with all its conditions, uh, plus whatever conditions we mentioned above, phosphoric acid, etc. Um, Now, the real issue is, what do you get? The double bond is going to go away. So I've removed the double bond. Okay, that's gone. Now the issue is you have these two carbon atoms. Where would the H get attached and where would the OH get attached? Now you're going to get two options, and the two options are that's one of them. The other one is that the double bond is going to go away, and the H would get attached on the right side, and the OH would get attached. I mean, this is the same one. The H would get attached on the right side, and the OH would get attached on the left side. So there are two totally different molecules that are possible if you have an unsymmetric alkene and you start doing an addition reaction. This one is propane 1-ol, whereas this other one is called propane 2-ol. Okay, this other one is called propane 2-ol. Uh, is this clear to everyone so far? Why you're getting two different molecules? Mohammed, Ethan, is
Yes.
this clear?
Yeah.
I says you're getting two different molecules. Now, one of them is going to be your major product, the other one is going to be your minor product. The major product is this one. Major product means that there's going to be a higher probability of getting this. And the minor product is going to be this one. Now, how did I decide which one is going to be formed in a larger quantity? Why would propane do all? And let me just confirm. It's going to be propane 2-ol. That's your major product. So how did I figure out that propane 2-ol is going to be my major product? Now there's a rule which is called the Markovnikovs rule, and the rule simply states that the H atom goes to the carbon atom in the double bond, or H atom is added to carbon atom in C double bond OC, which is already bonded to more H atoms. So which is already bonded to which is already bonded to more H hydrogen atoms. So if you look at the two carbon atoms, go back to the start, look at the two carbon atoms, these two over here. You get these ones. This one is bonded to two H atoms, and this one is directly bonded to just one H atom. So what you're going to figure out is that if you are trying to add H and OH, the H would go with the H would go with the carbon atom that's already bonded to more H, and the OH would go to the carbon atom that's bonded to fewer hydrogen atoms. Okay, right now just try and understand what the how to use the Markovnikovs rule. Why does it happen? We're going to discuss that in detail in the next class. But is this point clear? That whenever you have an unsymmetric alkene and you're doing a reaction, addition reaction, and you have H and OH or any molecule, any addition reaction is happening, the H atom always ends up with the carbon atom that is already having more H atoms. Mohammed, is this clear? Isa, Ethan, is this clear?
Yes.
Yeah.
Okay, so next class we're going to discuss what's the logic behind the Markovnikovs rule. Why does this happen? Why is there a greater chance of this molecule forming? You get this one over here. Why is this the major product? Okay, so let's continue with this in the next class then. Okay,
All
so
right.
take care.
Thank you.
Okay, take
Thank
care.
you.
You too. Bye bye.
Bye bye.
Bye.